Alright, so begins another draft science video presentation. A couple of subjects, maybe a little on lensing, a little on, I don't know, electron beams or cosmic rays or something like that. And I guess to start, something completely different. A subject, aliens. Yes, what's out there? What's it reasonable to believe is out there? So anyway, I really don't much like these chat things, live rooms. But anyway, this AB science guy, who is a still, I don't know, graduate student? I don't know. He's teaching college physics, so seeking a doctorate, I guess. And so, pretty good physicist, kind of physicist. And although he's holding a vial, like he's a chemist. Anyway, it's green stuff, so it's physics, right? If it's green in the vial, then it's physics. But anyway, so I did post a comment, and he, got around to answering it eventually. And they answered it in the comment section and still messed it up. It wasn't that complicated a question. Maybe I should try to copy, I copied it here somewhere, I think. Making neurons, that's it there. I guess I could post it in, I could post it in the comment section, just not post it as a comment, right? So anyway, they deleted it, which seems kind of bizarre, out of the chat, so it's not in the live chat anymore. It's not in the live chat anymore, right? It's just not there. It wasn't in the, if you get these stupid choices of the live chat replay or the fake chat replay, the top chat replay. What is that? So that's where such as potential spam, right, may not be visible. So all messages are supposed to be visible, but obviously they're not. Because mine's not visible. It's not visible to me anyway. We could argue. No, I don't want one of those choices. Forget it. So yeah, just not here. Well, anyway, it wasn't all that big deal. It clearly wasn't something that should be deleted. So I don't, what the game is, who knows, blah 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 blah. So we'll just go down here to the comment section, and I'll post my comment, and then you can see that was all it was. So I said, what's the most intelligent life form on Earth that contains no neurons? Question mark. So that was a question. And I say, evolution only made neuron-like cells once. That is, there's no other organism on Earth that contains something like a neuron. That can do this electrical brain thing. None. I mean, all of the intelligent life on Earth has got a common ancestor, and it only happened once. Eyeballs happen, they say, maybe 7 or 8 times. Different versions of a photon detector, but neurons only once. So if it wasn't for that one event of accidentally falling on the neuron, and again, it's all accidents, right? They're just mutations creating this electrical cell. There wouldn't be any. There wouldn't even be sharks. There wouldn't be anything smart on planet Earth. Anything that was doing any thinking at all. Or feeling, which is good. Excellent. But anyway, why do you think the rest of the universe is making neurons? Because he basically speculated. He did the same old tired Carl Sagan-esque kind of bullshit. Billions and billions of stars. It's just gotta happen. No, it doesn't just gotta. Yeah. I know. It's. Here we're sitting here, and the bias is, we win. We gotta have something, and we assume that. Well, it had to be winnable if we won it. But every lottery winner is kind of just saying the same thing, right? He's in the same position. Should he say, oh, it was really easy to win? Even though I had 1 in 10 trillion odds of winning, I won. And I should say, it was easy. It happens all the time. No, it doesn't happen all the time sometimes. Sometimes it only happens once. Sometimes no one wins, right? It's so hard to do. So this idea that life just flies out of matter, matter just can't wait to turn into a living thing, is a silly notion when you think of how many one-time events that are built into our structure. One time, a cell ate another cell and didn't digest it, kept it as a nucleus. One time. It didn't happen more than that. It happened once. All right, anyway. So it's just not very good science, frankly, these glib answers to questions. All right, so I'll play some of this, and he goes on about Monsanto a little, so I might as well do a little editorializing in defense of Monsanto.
And sometimes I agree with them, right? Especially when they're talking about anti-vax. No, I'm not an anti-vaxxer. Don't kill me. They talk about the evils of the pharmaceutical industry, and you kind of go, well, yeah, of course the pharmaceutical industry is evil, but yeah.
See, of course, I don't know if it is really evil. I mean, it's like any other industries. They're all trying to compete with each other and make the next Viagra or whatever, the little magic pill that they can get a lot of money for. Obviously, their successes have to pay for their failures, right? They spend a bunch of money researching stuff, and some of it doesn't work out, and they spent, millions and millions of dollars, and they have to somehow make the money back. And, they're not any more, say, profitable than the oil industries or all these other industries. You could point airplanes, all kinds of things to make lots of gratuitous money. But airlines are another good example because they have whole periods where competition drives the prices way down. They all lose money, and so then when the failures fall out, they have to they have to pay their debts. So they have to raise the prices to fix all the bad years they had. So a lot of good years, a lot of bad years. So it's not any worse than any other industry. And all of this, these scientists should be a little bit skeptical of all this hysteria, right? Because of the hysteria, even though, more people die of food poisoning every year than the coronavirus, and mostly related to seafood, 10,000 deaths in America alone, something like that. And you can fix that with irradiation, right? Irradiating food, perfectly rational thing to do, but a bunch of pop culture hysteria. Oh no, we can't do this. It's going to be radioactive. It doesn't matter what the science is. They've just done something really stupid. And and then the other examples are like Monsanto. I don't know who invented it. I don't know who came up with it, but they had this really great potato. That created a little bit of an enzyme that was essentially a virus to potato beetles. So they didn't have to use pesticides. It was like anti-pesticide potato. You don't need pesticides anymore because it makes all the little bugs sick. But it's completely benign to human beings. It doesn't, it's not a chemical that's going to bother our hormones at all, blah, blah, blah. It's not a pesticide. It's like a virus. And it doesn't affect us. So brilliant idea, but because all this anti-GMO hysteria, it's not implemented. So you're just pro the very industry you're saying is bad by saying make more pesticides, do it the wrong way more, because we're gonna have a big hysterical overreaction. And we see it all the time. I mean, remember all the hysteria about the silicone breast implants and all that kind of crap, and it all turned out to be crap science. I mean, but anyway, go ahead. Do exactly what you shouldn't do, which is do bad science right in front of the people who fall for bad science.
So you kind of have to agree with certain things, because there are, in any conspiracy nonsense, there are grains of truth. Right? Big corporations are...
No, there really aren't. There's a ton of conspiracy theories that have not a single grain of truth to them. Not a single one. Like, we didn't land on the moon. It's not a single grain of truth there. There's just people desperate, just absolutely desperate to deny science.
Generally dicks. Big Pharma are dicks. Monsanto is an evil company that should be burned.
What the hell is it? Monsanto should be burned to the ground. Why? Is it some kind of much worse player than the rest of the bad players? I mean, just, look what they did to Owens Corning, right? A company that 50 years ago, when they didn't know asbestos was dangerous, okay, they still had their employees wear masks because they knew this stuff couldn't be good for you, right? But they didn't know. And they crucified it, destroyed the company. A perfectly good company just completely destroyed it. For no malicious act. There was no malicious act. You know, this is, it's like General Motors being sued for $270 billion because a truck hit a truck at 70 miles an hour and it caught fire after the guy was already dead, right? No smoke in his lungs, right? He was already dead from the accident. And some loony jury awards whatever it was, $27 billion or some silly fucking amount of money. I mean, the world is full of a bunch of bad science is running the world, and here this guy, instead of editorializing about how all this bad science is fucking everything up, he's sitting there defending. There's a grain of truth. No, there isn't. There's a grain of desperation. The religious fucks and the woo-wooers, are so desperate, and you're feeding them
to the ground. But that doesn't mean, and I think Ben Goldacre says that quite nicely, as big pharma is shit, but it doesn't mean that magic beans are going to cure your cancer, right?
Which is pretty much a wishy-washy, nothing thing to say. So you basically just went right down, you walked right down the middle of the fence and didn't take a stand for anything. Bravo.
Right. So, I think I did have a thing going on. Oh shit, there's been quite a few questions. DraftScience. Oh, hello, sir.
So he must know who I am, right? So cool. All right, even though they deleted me. Okay, but all right. So in the comments section, I guess I don't have the other guy's reply. It was completely disconnected. I mean, it seemed like how do you have all right? You can't really do something too complicated in these stupid text marks, right? So it wasn't very complicated, and nobody could get the simple point I was making. So early in the video, he talked about aliens and made this sort of excuse that, it's they just can't get to us. They can't communicate with us because it's bad timing or some other kind of bullshit. But they're out there. They just can't talk to us.
What's the most intelligent life form on Earth that contains no neurons?
Okay, so just pause, question mark, pause. But no.
Evolution only made neurons like cells once. Why do you think the rest of the universe is making neurons?
Yes, good question. Because essentially there's no example of some other thing that makes it possible to do thinking. So here the Earth is covered with all these little bits, all these parts you could make something out of, and it's never come up with another formula that works. Nothing. There's just no example of a thinking machine, not made by us, on Earth except for the neuron.
I don't know. I would be wrong to assume that all intelligent life is, using neurons for the...
Yeah, I know, but the point is that all intelligent life would be using neurons. Well, what's the example of the other mechanism that works? What other possibilities do we see life just generating? Well, we see on planet Earth that life doesn't generate thinking machines with any regularity. It doesn't just make them all over the place. Hey, thinking machine, think. It doesn't do brain very well. It doesn't do it, like it just happens all the time. A new version of brain, another version of brain, another version of brain. Apple versus IBM. That kind of thing just doesn't happen.
Computational power that their intellectual organs, their equivalent of a brain.
Right, their equivalent would be made out of what? And be manufactured through what process? So I'm just saying the evolution of neurons into thinking machines is a whole separate category of hard to even imagine how it figured out how to do that, right? How it fell into creating that. And then even when you had a thinking machine, right, it wasn't until humans had the little quirk somewhere 50,000 years ago, the little thing went click, and they did the vocabulary thing, and all of a sudden that little tiny change, little click. Now all of a sudden they can do vocabulary, and vocabulary gives them this whole the ability to change the game dramatically, by storing information on rocks and tree bark and all kinds of different places, and being able to go to school and all this kind of crap. Do a bunch of experiments and figure out a bunch of stuff. And without language, that isn't possible. That's what's held back all the other mammals, all the other thinking machines. And they're stuck being incredibly ignorant. I mean, profoundly ignorant of their reality because of it.
Yeah, it may not be neurons, but it seems pretty likely, right?
It seems pretty likely, right? Based on what facts? Where's the evidence of the pretty likeliness? It seems exactly the opposite when you analyze it. When you look at it, it seems incredibly unlikely. I mean, it's sort of glaringly pointing out to you that life is a rare thing, not an automatic thing. The fact that all of the organisms have the same DNA molecule. Not even a slight variation on the theme. It's not like some other DNA molecule close, but not the same thing, made out of little different things. No, they're all the same DNA molecule. Every single living thing came from one living thing. That's what the evidence points to. Not that this thing arose all over the place. It didn't just poof, 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 poof. And again, that's with all these corpses. It's a junkyard just littered with car parts. But no cars poof out of it. That's an indication of rareness, not commonness, not routineness. It's exactly the opposite when you think about it. Okay, I'm being a little rude. So anyway, but these guys should be able to handle it because they have this thing called the shills. And so he's one of these shill members. And it's really deplorable, that these smart people would get into a room, like 10 of them, and they waste, 30% of the show just promoting each other. And then they just do a hatchet job. They all just call it the hatchet. So they take the dumbest buffoon science on the internet and, just make fun of them. Just ad hom them, just completely bad, in terms of behavior, just gross behavior in sense that, you don't expect it. You expect them to have really good arguments, not really shallow and stupid arguments. And, so it's just pretty bad. I'm just saying, it's pretty bad. But anyway, thank you for at least reading my comment. But again, this is such a bad medium for physics. I mean, doing science in the chat room, there's just something innately, you're just really not going to get anything important, are you? And again, sorry, his analysis isn't great. I like to say it was great, but it's not. So anyway, at least it's something, some interaction, right? So hopefully someday I can get debunked by the shills, okay? Because at least that'll be my opening, because then I can debunk them. Then I can do the same right back to them, Anyway. But, like I said, at least he did know who I was, right? DraftScience, he must have known who I was. So at least that's something. All right. So, comment. There's only one. There's Superior Mind agrees with me. So again, you can read the agreeable comments on your own. I'll deal with more of the ones that are less than complete agreement. I don't know what category to put this one in, frankly, but we'll see. I don't know why I have to. This text thing is so annoying. All right, how can you explain gravitational lensing? So, of course, I've done that, so I'll just repeat that there are subject videos, different categories and playlists. There's a link below. And those are probably the videos worth listening to if you're interested in that particular subject. But anyway, classical physics, as you know, suggests that we observe spherical distortion of space-time. They suggest and they state overtly lots of things that they don't have evidence demonstrating. And as I've pointed out, their theory for lensing is catastrophically flawed, in that they're not even paying attention to gravitational rules, which is gravity doesn't make a magnifying lens. It's completely the wrong shaped lens to magnify an object. It can't take diverging light from an object, a small thing this size, and the light diverges, and so you cast a big image somewhere else in space, and then you select that image, right? That's what our eyes do. You select the image and you bring it to a focus. So you're really looking at this big image created by a bunch of photons. Photons are going everywhere. It's creating a big image everywhere. So there's big images everywhere, so all over the place. And it's just about the way you capture one is doing this focus thing, where if you can take that big image and you put a lens in here, the lens does two things. It slows the light going in the middle down, and to compensate for the longer path of this light. So this light ends up being here at exactly the same time this light ends up being, I guess it would be here, the equal distant thing. It makes the distances more equal, keeps them in phase, so that you can have the same time of image here, the same time photon is the same time that ends up coming out the other side. And I'm just saying it compensates for the path length difference, so that the two beams, when they get here, the one that took this short path ends up being exactly in line, exactly in the same place all along the path, so that when you restore the image, the big image, and it has the same timing. So a gravity lens doesn't do this time changing thing, so that doesn't happen. Photons don't. Photons are supposed to, even by Einstein's rules, photons are the reliable thing. Anyway, and clearly what it doesn't do is bend light more on the outside, which it needs to, and less on the inside. That's a magnifying lens. Gravity doesn't do that. Gravity does exactly the opposite. It bends this light almost nothing because it's way out here, and the stuff close to the gravity, it bends a lot more. So obviously it won't go to a focus, so the theory is junk. Just isn't even possible. Now, the Einstein ring could just be a fluke, okay, of you just happen to have enough gravity to bend a photon over here, and by symmetry arguments that would be exactly the same amount to bend one over here, but the photon in a little bit would end up being bent too much, and the photon out a little bit would end up being bent too little. So again, you'd be out of luck. So the ring should be like 3 photons wide. Okay, the ring should be so thin that it would be impossible to see. Now that's what Einstein stated. Einstein said if there were Einstein rings, you're not going to see them because they're going to be really, really thin. What are the ones they have images of? Oh yeah, right. Big fat things. I mean, humongously fat rings. And then we have Einstein crosses, which really make no sense geometrically even. But yeah, their rings are these big, thick things. Big, blobby, uneven thing, and just a silly ring. Can't be done. And then they have this other thing where they say, oh, look, it's a round thing, and a round thing, and a round thing, and a round thing. Well, how could you make the image of the round thing? Right? Because the image of the round thing requires that gravity to do that magical thing again, where the photons that need to be bent more are bent less, and the photons that need to be bent less are bent more. So again, you're out of luck making a focus. So you could never create an image that could come to your focus, because the thickness of the image means that somehow you broke the rules of gravity, which is the stuff closest to the gravity bends more, the stuff further away from the gravity bends less. You've broken that law. So this couldn't happen. And again, why would this happen anyway? If it's equal, these two four are equal, it has to be equal here and here too. It has to be equal here and here too. by symmetry arguments. So the cross thing should never happen anyway. Very unlikely. See, the cross thing is dependent on them thinking that some huge gravitational object has non-symmetrical gravity. That is, that there's some black hole that, like the Earth or something, it's got a bulgy fat middle. So the gravity is uneven. And so the argument is that the amount of bending here and here, because they're further, it would be here and closer to this one. So the distance here, since there's more gravity, it's further away. And because there's less gravity here, because it's thinner, it's closer. And they just happen to be the same amount of bending, just by lucky happenstance. La 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 la. Ah, silly. Silly. Alright, our partial arcs, okay, we observe spherical distortion of space-time. Our partial arcs scattered around the gravitational lens. So again, they used the word lens. The lens is the wrong shape if it's a lens. It does rely on magnification. How could it possibly be magnifying? Again, by the gravity rules are the light you need to bend more, you're bending less. Can't possibly be magnifying anything. I.e. Einstein ring. Again, let's point out, Einstein said you wouldn't see one. Because it's going to be such a little tiny thin shred of space that'll have the right bending. Even looking at the pictures of gravitational lensing, can't really say that's just light reflecting. Well, it wouldn't be light reflecting, it would be refracting. My argument would be is that big gravity is going to have big symmetry. That is, it's going to be lots of symmetrical. There's going to be lots of consistency in the gravity. It's not going to be highly inconsistent. So it just seems to be pretty much out of luck. And if it were a fact, then we'd be seeing it all over the place. There would be little pieces of light shooting the whole universe would be covered with little bits of weird light coming from weird places that have been, distant objects that have been magnified all over the place, and we'd be seeing all kinds of distortions. Maybe distortion is a better word for that. Yes, and if it was distortion, they'd be all over the place. And the fact is all of these things that they say are lensing images, you can see in them that they have pieces of a galaxy or clumps. They're very clumpy. And they have this kind of the look of a smoke ring as it ages in time, where it gets all kind of distorted. And, it looks very much like something exploded, and there's a bunch of matter, that used to be a solid thing, and now it's broken into pieces. It has every appearance of kind of a smoke ring, or a piece of a smoke ring. So why wouldn't that be the more logical conclusion? And I would argue, yes, of course it would be the more logical conclusion. So, I guess I'll take a pause and be back for some cosmic ray conversation. Alright, should be back. Better check. Okay, looks like it. Alright, so I've been doing some looking at different things, accelerators, different cloud chambers, different ways of imaging energy, and there does seem to be something missing from the story as far as I'm concerned. So the idea of these cosmic rays is that there's these super powerful things. They're calling them protons now. I mean, that's the most common thing I've heard. And that even the Earth, sitting here, somehow they plow right through it and come out the other side of the Earth. All right, and, it doesn't make much sense to me that anything, any single ray could actually be capable of doing that. It just seems a little far-fetched. That, maybe it's possible the energy can go in and reflect off the Earth or something, but I don't think it's going straight through the Earth. But anyway, so, so the idea is this whole idea of electrons are protons, and the drag argument and how things get through space. And I'm just kind of becoming skeptical of the whole theory of electrons being in a beam, that's what you're actually seeing. So like the cosmic ray, you really couldn't tell the difference between force and a object like an electron. If the two things collided with something, how would you tell one from the other? Is there anything that would just give it away that this was a force? You know, the little bits moving the speed of light. I guess that's part of what gives it away, right? Is how fast is it going? Or an electron. Well, the electrons appear to be moving the speed of light. So when you push one through an accelerator, the electron is assumed to go, whatever, 15 meters, okay, and not lose any momentum. That is, not slow down at all, not be inhibited from moving close to the speed of light, very close. And so you end up with some, like, you can add more energy, but this is all you get. Instead of some chart where it gets, more and more faster and faster, there's just this little bit of increase you get for adding more voltage. So you add up millions of more volts, and you don't get any increase in the speed, the time it takes for it to travel the distance. And that sort of indicates to me that something else is going on here, and that actual electrons aren't really traveling. Now, another way you can look at it is that if you do an electrical experiment, with the little gold leaf that flips out, and you put a charge on it, you can bring a charge, so it starts off flat. So I bring something charged, positively charged will work. And what will happen is the charge will somehow, the radiation from the charge goes to the little ball. It creates somehow the opposite charge, right? It makes it negative at the ball if this was a positive. And inversely, you'd say here must be the positive end. So these two ends become positive and they repel each other because they're both positive. And this one can move. So it moves. Just say, I'm a like charge down here. So whatever the charge is here, you're transmitting it to here, in theory. And then you move this away, and this will swing back down. Now, if I move this too, and then I touch this, okay, which allows stuff to come from the ground into it, then the reaction, the state, will be maintained. And so that kind of makes you think that this is some kind of force that actually is the force the force is doing the transmitting. I didn't put an electron on here. I didn't send, when I bring this positive charge here, I'm not pulling electrons off or sending electrons to the object. I'd have to touch it to do that. And so all I'm doing is sending the force. I'm putting pressure in one end. And that's creating an imbalance in the object itself, where you could argue that because of the extra pressure, there needs to be extra electrons, and so it pulls the electrons out of the other end because of the extra pressure that's being created. So to balance itself, it moves the pressure, moves the electrons inside the object. All right. So how to illustrate this? What I'm tending to think is that cosmic rays aren't really. Go back to the balance argument. So you start off with objects. So the idea would be is if an electron was to hit another electron, what I'm saying is moving, that you really couldn't tell the difference. And then if I just hit it with a bunch of force, so if I hit it with extra little force, moving the speed of light, or I hit it with an electron, how are you going to know which one hit the thing? Because you can't see these things. And what you're going to see is this plow through something. You're going to see this move, but you're not going to see what caused it to move. And that's what they have in cloud chambers. They have some little trace that starts at a point and goes to another point. All right, they don't have, and all they're really seeing is something being moved. They're seeing the pool balls move, but they don't know whether it's moving because the cue ball, the cue stick hit the ball. You can't tell the difference. If I was just to show you the ball rolling, you couldn't tell the difference between a ball rolling because another ball hit it or because the cue stick hit it, right? The original force. So, in theory, what I'd like to be able to see is them to take electrons from a surface and make them move across really slow, like 1/10 of the speed of light, or 10% of the speed of light. Is there any experiment where they do a pulse of energy and they make the electrons move at 1/10 the speed of light? Because that I haven't seen. I haven't seen any examples of electrons moving really slowly. So they pulse it and then they go 15 meters away and they collect the pulse and they figure out that it took it 10% the speed of light to get there, because all of them come out being really close to the speed of light, like 90% of the speed of light is what they're measuring. Now I'd argue they're measuring it because it's a force and it starts and finishes, the time it takes is what's creating the less than the speed of light, but you're not really measuring the first hit of the wave and the first hit of the wave. You're measuring the average of the wave with the average of the pulse that you initiated. So there's some elements where you're measuring this last bit that was sent, and you're comparing it and you're thinking of it as a first bit sent, and it's a last bit sent. So obviously it's going to lag behind here. If you're expecting it to be here and the end of your pulse is here, then obviously there'd be a lag, because this is it's going to be, this time is when it was sent. These two times are the same. You can almost see that. And this doesn't proportional to that, so that's the lag. A little bit slower than the speed of light is being caused by that. All right, so anyway. So the point is that the experiments always rely on creating a potential difference, okay, between two objects. So you plus this and you minus this, and you expect this radiation to be moving in this direction, and that's how they're moving these electrons. They're saying, okay, let's feed some electrons into here and let them be pushed by that stream and then go through, because we're going to put holes in here, and so some of the electrons will go through the holes and keep moving in that direction. But the whole point is all this force is still going through the experiment also. So there's a bunch of cue sticks that are still poking as this, whatever this is moving. And what you might just be measuring is the force rather than the object itself, because you're only going to measure it by waiting to hit it again. Like I said, the only way they're detecting anything is they're sitting there sort of looking at a surface, like even in the atmosphere. They're saying, here's an atom in the atmosphere. And what they're doing is they're saying, well, a cosmic ray hits it, okay, and makes this do something. Pieces break off and scatter and all kinds. So they're not seeing the thing. They're seeing something else they're watching and saying, does this thing move or break? And if they see it move or break, they're saying, well, what must have hit it was this thing, a proton. When no, what could have hit it was just a lot of radiation, a stream of radiation, a stream of force, a photon, a photon with a very fine. So the other part to understand is that this gamma radiation, when you get past X-rays, the whole idea is what you're saying is there's a point where you get the frequency so high that it's essentially a straight line of force. That it's completely. It not only has no polarization, that is, the little bits they lose all of this distance thing between them. So their polarization's getting narrower and narrower as their frequency gets tighter and tighter. So as I make the frequency, you can see that, right? Yeah, so as I make the frequency smaller and smaller and smaller, I'm making the polarization, that is the amount of out of alignment with a dead straight line, I'm making it more and more straight. So as I make the frequency tighter, I'm making it straighter and straighter. And theoretically, now, because it has so little polarization, right? It's going from big polarization, like normal visible light has a polarization that's maybe 2,000 atoms, okay, wide. That is, the spread in the bullets is 2,000 atoms. When you're getting to gamma rays, right, the spread isn't an atom's worth. It's smaller, smaller and smaller. So it could be 1 electron's worth. It's such a tight formation of energy that it's just plowing into 1 electron, and it pushes the electron, and it pushes the electron, and pushes the electron. It keeps hitting it in one direction. It keeps applying more force. So in essence, my theory would be, when the electron is neutral or stationary, the idea is it gets hit with as much from one direction as another direction, right? So there's exactly the same amount of stuff hitting it. And the trick is though, if I add one of these gamma rays, I'm creating a whole new beam of stuff on one side, and the only compensation the other side has is the fact that once I start getting this thing moving, it's going to plow into more of this. Okay, then it's going to be pushed by this. So as soon as I move something, I'm creating imbalance, and there'll be pressure against that movement. And so I'd argue that there's always a drag problem for electrons and protons, that theoretically they can't move anywhere near the speed of light. And so it can't be electrons and protons. It's just force. It's just these rays. And the fact is if these rays hit electrons, then it'll look like it's a high energy electron. But it's really not. It's just a force hitting an electron, pushing it. So like a mu meson would be just an electron that was up in space, right? So it was sitting there minding its own business in space as part of an atom. And what happened is one of these gamma rays that's, again, it's not oscillating 2,000 atoms worth. It's really a fine little ray of frequency, a bunch of cannonballs coming right after each other, and they're hit dead center on the target each time. And so they just keep hitting this electron. They keep hitting it, keep hitting it, keep hitting it at the speed of light. And so as the electron goes faster and faster, the amount of pushing slows down proportional to how fast the electron's going. So the slower, if the electron is dead stop and it doesn't, if I'm just reflecting it, let's say, and I just hold the electron there, well, this might only take 1/1000th of a second, for all of this ray to get used up. But if this electron starts moving, then it's going to be maybe 1/1,000,000th of a second, okay, it would take to run through all those cannonballs, because this is moving as the cannonballs are moving. And so the forward pressure takes longer to get through all the bullets, because so it's just like you moving. If you could run really, really fast and somebody shot a gun, you could see that the faster I run, the less frequency the bullets have, the longer it takes between each bullet that hits me. If I can run fast enough, I can outrun all the bullets, right? But nothing can go faster than the force, so obviously I can't outrun them, but I can delay when they hit me rather dramatically if I can run fast enough. And that's what the electron is doing. The electron is being pushed by a ray, and the ray, as the electron goes faster and faster and faster, it takes longer and longer and longer for that ray that was only 1/1,000,000th of a second long is now, could be a second long, depending on how long the ray starts off as being. So there's no discussion in conventional physics about ray length as an explanation for energy. So again, I sort of pointed this out in the other video with the linear accelerator. The idea is when they measure how fast the electrons are going, the speed doesn't change. It just, it's whatever, 97% of the speed of light, and it goes to 98%, but it doesn't change much, even though they're putting a lot more energy in. But if they measure heat, Okay, if they measure the heat, how high of the electrons, somehow the electrons are making more heat. So it's supposed to be the same number of electrons because the pulse is a set thing. The amount of electrons in the stream is supposed to be constant. The volume of electrons is a constant. And their speed is almost a constant. So why would there be more heat? And I think the obvious explanation is there'd be more heat because the what's really hitting the target now is the force. The force causes heat because the force is it's a real thing, and it's going to agitate. It's going to add charge to the. You see, the charge doesn't go up either. So when they measure the charge doesn't move. See, I'm not sure of that one. They're measuring the time it takes. They're measuring the charge, and they're measuring heat. Yeah, I don't remember what the charge did. Charge might have gone up. So anyway, that's just indicating that they're just charging. They're just sending force into it, and the force is agitating the electrons, which is making them, because they're going to have more pressure between them. You're increasing the amount of pressure between the electrons, but you're injecting a bunch of extra force that gets caught in traps and pressurizes all the electrons. So anyway, it's draft stage. But again, I'm really, if anybody has any evidence of slow-moving electrons, I'm looking for an experiment that shows electrons going from point A to point B in some really slow manner. And it can't be like through a conductor, because you know you can make conductors that are really bad, you know, and the electrons are banging into stuff all over the place to get from point A to point B, the force. And so that's not an example of electrons actually moving. Some free space where electrons in a vacuum move really slow. All right. So enough of video, I would say. So till the next time. I'm just saying that a force completely can replace any object they call a particle moving, because it would do exactly the same thing, because our detecting always is just, we're watching the 8-ball, and we can't tell the difference. The 8-ball moves. We can't tell the difference between the stick hitting the 8-ball and another ball hitting the 8-ball. The reaction is going to be the same thing. It's going to be movement. We're just detecting movement in something we're measuring, and the cause of the movement could be the force itself. And the force moves the speed of light, which makes sense. All right, so till the next time. What the hell is that? Oh, that's the magnet there. Oh, I get it. I'll put this back where it belongs, so to speak. All right, so till the next time and such. See, there's a radial force coming off the magnet. No swirly bits, people. Nothing swirling around a magnet. See, the other physics guy says he knows what a magnet is, and yeah, that was interesting too, because he was going to explain magnets, and then he said, "Oh yeah, I really can't explain them," which was kind of funny, especially to somebody who's teaching grammar school or something, right? Like a grammar school guy asked him how he would explain magnetism. He's like, "Oh yeah, that's easy," and he thought about it. He says, "Well, no, it's not really easy," because yeah, their crap is just so dependent on Faraday's mistake. Faraday's mistake was to say these magnetic lines are like conductors, that those iron filings are there because there's some stream that they're in, you know, when no, it's because the magnet itself is a pushing force, and the push makes the iron into magnets, and they repel each other. I mean, all the iron filings have exactly the opposite magnetic orientation to the original magnet. And it's just funny how, I mean, you should see it, because look, they're standing on end too. Why would they do that? Why would they stand up on end? Okay, if it was a force that was going this way. Why would they do this? You know, they would do this. They wouldn't do this. Anyway. Okay, so till the next time and such. And so forth and whatnot. Yeah, I think it's enough.